Last time, we encountered some curious behavior. The diagonal matrix, 3 times the 2 by 2 identity, had a single eigenvalue, lambda equals 3, and a two-dimensional eigenspace, which was all of R2. While the upper triangular matrix, 2, 0, 1, 2, had a single eigenvalue as well, lambda equals 2, but a one-dimensional eigenspace spanned by the unit vector e1. So in order to explore this behavior in more depth, we need to recall a basic fact from algebra. The theorem states every polynomial p, which is going to use lambda as the variable, equals lambda n plus an minus 1 lambda n minus 1 plus dot 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 plus a1 lambda plus a0, which is a degree n polynomial, has a unique factorization into powers of linear terms, lambda minus lambda 1 to the m1, lambda minus lambda 2 to the m2, down to lambda minus lambda p to the mp, where each of the lambda i's are complex numbers, and the sum of the exponents is n. We call the numbers mi the multiplicity of the root lambda I. So the slogan here is that every degree n polynomial has n roots counting multiplicities. So with this in mind, we can make a couple of definitions that we can use to explore the behavior of repeated eigenvalues and the dimension of the eigenspace. So we let A be an n by n matrix. This tells us that the characteristic polynomial is a polynomial of degree n. So the theorem tells us we can factor this polynomial as a product of linear terms. The roots of this polynomial, of course, are the eigenvalues of our matrix A. First, we define the positive integer mi to be the algebraic multiplicity of the eigenvalue lambda I. Second, we define the positive integer, the dimension of the eigenspace E sub lambda I, to be the geometric multiplicity of lambda I. So as a note, the matrix A minus lambda I times I always has a non-trivial solution to the homogeneous equation. So the geometric multiplicity is always at least 1. Now, our examples from last time tell us that the algebraic and geometric multiplicities do not always agree. As we saw with the matrix A, with columns 2, 0, and 1, 2, the eigenvalue 2 has algebraic multiplicity 2, even though the geometric multiplicity is 1. So this tells us that the geometric multiplicity can be less than the algebraic multiplicity. However, the matrix 3i has a single eigenvalue 3 with algebraic multiplicity 2, and the geometric multiplicity is the dimension of E3, is the dimension of E2 is 2. So we can see here that the algebraic multiplicity and the geometric multiplicities agree. In general, this sort of behavior applies to all square matrices. If we let A be an n by n matrix, if lambda is an eigenvalue of algebraic multiplicity m, then the geometric multiplicity of lambda is at least as large as 1, but no larger than m.